Okay, welcome everyone. So in this video, I want to connect some of these ideas that we've been discussing and illustrate them in a nice example. So we've been discussing quadratic forms and how we can find a symmetric matrix to represent that quadratic form. And then we talked about how we can diagonalize symmetric matrices, what's particularly special about those cases, and how we can apply that process to diagonalize a quadratic form. So the example I want to consider is, let's consider the quadratic form q of x, which is equal to 2x1 squared plus 6x1 x2 minus 6x2 squared. So this quadratic form initially has what we're going to call a cross product term, or this mixed term, which is the 6x1 times x2. So our task here is to try and find the change of variable, which we're going to define with an invertible matrix P. In this case, P is going to be an orthogonal matrix that is going to allow us to re-express this quadratic form in an equivalent but diagonal form. So in other words, we don't have this mixed term any longer. So the first step would be to identify the matrix of this initial quadratic form. So in this case, that matrix, recall, we get the first diagonal entry 2 from the coefficient in front of the x1 squared term. We get the other diagonal entry from this term, which has the x2 squared term. The coefficient in front of that is minus 6. And then these off-diagonal entries we get from this cross product term. The coefficient here is 6. So we divide that evenly in half. So we have a 3 in the A12 position and a 3 in the A21 position, making this a symmetric matrix. And then you can verify that matrix A has eigenvalues. Lambda 1 is equal to minus 7 and lambda 2 is equal to 3. And the reason why we're finding eigenvalues for this matrix of the quadratic form is because we want to diagonalize the quadratic form by finding this change of variable matrix P, which is going to be the same matrix P which diagonalizes matrix A. So this matrix P is going to consist of orthonormal eigenvectors for matrix A. So we need to find eigenvectors, and matrix A is the short story. So we first find the eigenvalues, and now we're going to be able to identify an eigenvector for each of those eigenvalues. And so, for example, working with the eigenvalue, lambda 2 is 3, we can subtract 3 from each of these diagonal entries, giving me a minus 1 and a minus 9 here. And then think about what are the homogeneous solutions to that resulting matrix, which gives us a solution x1 is equal to 3x2. So that's where this vector v2 equals 3, 1 comes from. And we can similarly find an eigenvector corresponding to lambda 1 is equal to minus 7, which happens, one such eigenvector happens to be v1 equals minus 1, 3. And so now these two vectors, v1 and v2 that we found, we would want to express them as a set of orthonormal vectors that spans the same space. Because these two eigenvectors come from distinct eigenvalues, you can verify that they are already orthogonal with each other. If they were not orthogonal, for example, we had one eigenvalue which had multiplicity 2, then we may need to do the Gram-Schmidt process. But we don't need to do that here because these vectors are already orthogonal, but we do need to normalize them. So this matrix P, this change of variable matrix, we're gonna take each of these eigenvectors that we identified and normalize them. So this first vector v1, it has magnitude square root of 10. So that's why we scale each of those entries by 1 over root 10. And v2 happens to have the same length, square root of 10, so we also scale the entries in vector v2 by 1 over root 10. So our change of variable matrix P has first column minus 1 over root 10, 3 over root 10, and the second column is 3 over root 10, 1 over root 10. And let's just recall how this is going to give us a matrix, a diagonal matrix D, to represent the same quadratic form. That is, if I replace X with P of Y, where P is this orthogonal matrix that we've chosen, then x transpose AX is equal to PY transpose A times PY. So we're just replacing each of the x's with our expression P of Y. And now this transpose, PY transpose, we can rewrite as Y transpose, P transpose, and then we multiply by A, P, and Y. And so now this P transpose A, P, since we've chosen P as this orthogonal matrix, we get the diagonal matrix D, which is going to consist of diagonal entries that come from the eigenvalues of our matrix A. So let's summarize this below. Now our new quadratic form, which we can now write in terms of this new variable y, our change of variable, is going to equal y1, y2 as a row vector times this diagonal matrix D, which has entry -7 and then 3 times y1, y2. So this can be written algebraically as the formula -7 y1 squared plus 3 y2 squared. And so this diagonal form of the quadratic form that we have down here is going to be preferable to the form that it was given initially in a lot of situations where we may be interested in finding eigenvalues for the matrix of the quadratic form or inverting this and so on. That's going to be much, much easier when we're working with a diagonal matrix as opposed to the symmetric matrix that we started with. And this process of diagonalizing the quadratic form, we can do this for any quadratic form. So I just want to state that general result on the next slide. So the process that we went through in the previous example, that is one case of showing why this theorem, the principal axis theorem, holds. So if A is a n by n symmetric matrix, then there is an orthogonal change of variable given by x is equal to P of y that is going to be able to transform any quadratic form Q of x equals x transpose AX, where A is some general symmetric matrix, into a quadratic form Q of y is equal to y transpose dy, where D is only consists of squared terms and there are no cross product terms. So D, in other words, is a diagonal matrix. And this change of variable matrix P, we can choose this to be a matrix whose columns are the orthonormal eigenvectors of the symmetric matrix A.